Hi there. Thank you for attending my virtual lecture today. I'm Tieyuan from Penn State University. So today I'm going to introduce the FORESEE DARS array in Pennsylvania. As a picture in the left corner, the orange line indicates the fiber optic cable across the whole state college in Pennsylvania. So I'm going to present here all the recording results from this DARS array. Before I jump into the data, I want to start with the definition of DARS, and then how can we convert this cable to the seismic sensors. So if you look at the black box, this represents the integrated box, was connected to this fiber cable. So DARS box keeps sending the laser pulse because the impurity of fiber optic cable, the sending laser pulse gonna be backscattered back to the box, was received by this box, okay? And if you have a seismic wave propagations from earthquake or active source energy, the wave gonna perturb this fiber cable by compress or stretch. So in that sense, this red signal gonna be perturbed to this green signal. The difference between red and green signals in the phase or amplitude gonna represent this seismic energy. If we repeat this calculation for each impurity point along the fiber, so we can convert the whole continuous fiber into discrete seismic sensors. Compared to conventional geophone indicated as this yellow in the right, the DARS actually have several good advantages. For example, DARS can have 1,000 or 10,000 horizontal sensors easily, which measures the strain or strain rate. DARS can be very dense in a local region, with a meter scale. DARS also can have a very easy power supply. We only need to have the powers for the DARS integrated box, okay? And all these features make the DARS actually the great candidate for the seismic study, especially for the long-term deployment in a harsh environment. In the early experiment, colleagues use a fiber deployed in this trench, to increase the coupling with the soil, and then connect with the integrated box for the near surface or earthquake study. Recently, colleagues also to think about if we can use a dark fiber to replace the new fiber to conduct the same seismic study. Most previous experiments have been developed in California, so here. So today, I'm gonna show you the experiment from Pennsylvania. So we named the FORESEE array called the Fiber Optic for Environmental Sensing. This was developed in State College, Pennsylvania since April 2019. So we continuously collect the DARS data until today. So we use a dark fiber owned by university was in the conduit as this black line here. So this is about 1 meter depth. So if you look at this orange line here, so this is about a 5 kilometer long dark cable. Speaking of resolution, so we have 2 meter spacing, gauge length is 10 meter, the sampling rate is 500 hertz. Okay, so if you get a rough calculation, so we're gonna end up about 2,500 sensors. But because this cable was in the conduit, so we don't have a very accurate location for each sensor. So we conduct this tap test to measure the 120 location accurately. And then we interpret all this location into the whole cable. So at the end of the calculation, we end up with 2137 sensors. Give you one example of all this DARS data. So this is my channel number from 600 to 1600. This is about the campus. And then this is outside the campus. You may find some very strong events. This is associated with the vehicles. Okay, so this is very typical noise condition across the state college. So a little bit noisy in the two sides and also in the middle. So this is a very interesting example from the full step detection. So you see the black line here represent DARS cable. So my student, this is one school bus station. So my student did an experiment. He sat down here, and then he found a school bus stop, and then people got off the bus. And then a group of 7 people walked down to south. You see, actually our DARS pick up this 7 people energy as a linear line. The speed, walking speed is about 1.4 meters per second. You can measure from the slope. And then a few minutes later, my student Junzhu actually walked to the same direction, but with a much weaker energy. Meanwhile, another person worked the opposite way. You see, we can use a slope to determine all these human being full step. This actually gives us a very good confidence to use a dark fiber to detect this very weak vibration energy. So during last few months, so especially from the March to June, we look at the seismic noise variation to understand how we can use the seismic noise to help us to understand these different COVID-19 environments. So as you can see here, the red zone represented the stay-at-home order in Pennsylvania. We found a big noise reduction across all frequency band. And then after the phase yellow, we found some noise actually recovery. For example, 10 to 50 hertz, 50 to 100 hertz. You see noise have a very clear increase. But when we look at from 1 to 10 hertz, we didn't see that increase. So this actually tells us people didn't move much after the phase yellow. People more conservative. But they drive the car outside. So you can see the traffic noise, vehicle is a lot. This is a very interesting observation from this dense array. And also if you look at the spatial variation, so I also use a different frequency. This is from the March, April, and then June. You see a very big noise reduction on campus because less students, less school activities. After the phase green, so you see a little bit recovery. So if you want to know more research, please go to the Junzhu's talk in this afternoon. And we can also use the ambient noise for subsurface imaging. So as you can see, after you do all this noise cross correlation, so we can end up Green's function for each day. For example, for this particular week, there are no much near surface variations. So you see the Green's function quite stable. So we're gonna expect if there are lots of raining days or groundwater variations or some other variation in near surface. So we're gonna expect this Green's function gonna have an indication. DARS also registers these earthquake signals. For example, this is a very local earthquake close to the campus. So the DARS fiber registers this signal across all these 2,000 sensors compared to the nearby seismic station. This is another very exciting results from our FORESEE DARS array. As you can see, this is the radar map to indicate how the thunderstorm crossed the state college. And then I have animation trying to tell you how this lightning thunderstorm interact with the solid earth and then be detected by this DARS array. You see all these events cross all sensors. This represents a thunderstorm. This is another thunderstorm. This is a strong one. And the linear events represent the vehicles. I put a sample example here. As you can see, we have very weak energy, some very strong one, and also some complex one. So this can give us some information about how the wave propagated in the near surface or the complexity of this thunderstorm. So this is very unique in Eastern US. So we have lots of weather events in the Eastern US compared to Western US. So we can take advantage of very dense stars array to help us understand these weather events or help us to use a weather event to study the solid Earth. So for example, take advantage of this dense array, we can see how the wave propagation across the array. You see this energy going up, going down, this represents the first event. So my second event, energy gonna propagate from this side and then all the way down to the last sensor here. So this can help us to understand heterogeneity in the near surface. So my student and Sam worked very hard to extract all these 120 thunderquake events. So we can use the location with the ray tomography, travel time tomography, so we can end up with this velocity anomaly. For example, low velocity, high velocity to understand the local geology. If you want to know more, please go to Sam's talk in the afternoon. So to summarize what I'm showing here today, so we show the FORESEE array with a dark fiber is with low cost and low maintenance. We show the dark fiber also have a greater sensitivity to the very weak energy and also some new signals, for example, from the weather, thunderstorm, thunderquake, full stop, COVID-19 noise. I hope my results can shine lights for the future DARS array in Eastern US. For example, we can use the very dense dark fiber in the urban area to study the geology in the urban city. That geophone is not very easy to deploy in the past. And also can use it for geohazard study, especially sinkholes are very common in Pennsylvania, Florida. And also the groundwater level is more variable in the Eastern US compared to Western US. And also the weather events probably bring another opportunity for seismologists plus this dense array to understand subsurface or near surface and also the weather events as well. So with that, I conclude today's talk. If you have any questions, please let me know. We'll be happy to take some. Thanks.